Thank you very much, Ron. And the motivation for this topic for me was the interesting property of least square solutions. On the left, you have a matrix of full column rank, so the least square solution is unique. On the right, you have let's say the matrix has n columns, then on the right you have a submatrix, n by n, which is non-singular. They do not all have to be in one place, so you can imagine that the rows are scattered. And there is the corresponding portion of the right-hand side, and the solution of this subsystem is, we can call it a basic solution. This is like the terminology of linear programming. And it makes sense that the least square solution will be a convex combination of the basic solutions, but the weights surprised me. The weights are proportional to the square of the determinant of that basic matrix. And where else do we see squares of determinants? Well, one example from calculus is the cross product. And here is what we teach students in calculus, the cross product of U and V. And the area of the parallelogram spanned by UV is the norm of that cross product. But if you do Pythagoras on that vector, you get that the area is the square root of the sum of squares of areas. Each one of them is a projection of the parallelogram on one of the coordinate planes. So in this case, I can write that A is the square root of AX squared plus and so on, and AX is the projection of the area on the YZ plane. In general, for general matrices, not a full column or row rank, and here you have a matrix A on the left, and you have the matrix is n by n of rank R, and I highlighted an R by R submatrix that is non-singular. And on the right you have the Moore-Penrose inverse, and what it does, it finds for every linear equation involving A, it finds the least square solution of minimal norms. So this is very important in application, especially in statistics, where we are looking for minimal variance estimates. So the corresponding results for the Moore-Penrose inverse is that it is a convex combination of inverses of matrices that you find in A, R by R matrices. The position gets transposed, but the weight is still the determinant square. So this is, okay, now if we go back to A, the inverse of the inverse is the original matrix, so we get that A itself is a convex combination of inverses of inverses of maximal R by R matrices of the Moore-Penrose inverse. So this is the most general maybe and the most useless factorization, decomposition of a matrix, and I cannot see of any application except that the one of them of maximum volume would be the best R rank approximation of A. We'll come to it later. So here is the definition of the volume of a matrix, and it is the zero if the matrix is zero, and otherwise it is the square root of the sum of squares of determinants of maximal non-singular submatrices. This applies to all matrices, numerical or symbolic, and the next definition is just numerical. So it is the product of the singular values of A. And as I mentioned, definition 2 applies to non-numerical matrices. Now why volume? And here is one reason, that is, okay, I have a small perspective is that 60 years ago, no one in linear algebra knew what singular values are, even though they have been known for integral equation for about 100 years. Also, now every undergraduate, at least one that uses books by strength, knows about the 4 subspaces. And this also have been known in integral equations in 1905 in the work of Fredholm. But the idea is that if you think of a matrix as representing a linear transformation, then it goes from one subspace, the range of the adjoint, to the range of A, and in a way that is one-to-one and onto, so it is invertible. And every unit cube in the range of the adjoint of A is mapped by A into a parallel type. It's no longer a cube necessarily, but it has volume A as defined above. And more easy to see, to prove this I use the singular value decomposition, but more easy to see that every ball of volume 1 is mapped by A into an ellipsoid of volume of the volume of A. So that's a good reason to call it the volume of A. And next I show that if this concept is not necessary if the matrix is of full rank, because then it is just the Gramian that we also have known for more than 100 years. So that if the matrix is a full column rank, for example, then we take the determinant of the W transpose times W, and the square root of that is the volume of the matrix. So for full column matrices, it is not necessary, or it is a generalization of the absolute value of the determinant. Now, in linear algebra, a common tool is the factorization. We factorize a matrix into a product of a column matrix and a row matrix, a matrix with linearly independent columns times a matrix of linearly independent rows. The number of columns and the number of rows is the rank of the matrix. So I call this a full rank factorization. And in this case, the volume of A is just the product of the volumes of the C and the volume of R. So again, I could have used the gram determinant to get this result. Examples of full rank factorization are the singular value decomposition, the QR, something new that's called CUR, and so on and so forth. Okay, I'll skip some stuff. Here to give you an intuition for the singular value decomposition. This is a picture of the singular value decomposition, the so-called slim form that you get from Maple or MATLAB or Mathematica. And the matrix A on the left is M by N. The rank is R. So it is a product of 3 terms, U, matrix with orthonormal columns. And this is an orthonormal basis for the range of A. And a diagonal matrix with singular values on the diagonal. And then a matrix V transpose with the rows of V are orthonormal basis for the range of A transpose. The columns of U and the columns of and the rows of V are the basis, or if you complete them to the null spaces, these are the bases in which A has the minimal representation. The matrix A is represented by the R numbers on the diagonal on sigma. And the way to see it, and actually the U's are the eigenvectors of A transpose, and the rows of V are the eigenvectors of V transpose corresponding to the eigenvalues, which is the square of the singular values. A takes a cube of sides V1, VR, so it is a unit cube, into a cube of sides sigma 1, U1, and sigma R, UR, and this is why the cube is mapped into in this case to a cube of volume A, not product of the singular values. But these concepts are unitarily invariant, so that if you rotate the cube, you get something else, but the volume gets translated in this manner. Any unit cube in the range of A transpose is mapped into a parallelogram of that volume. Singular values go very well together with angles. And in the geometry of subspaces, there is a concept called principal angles. Again, this is something that has been known by statisticians since the 30s, the work of Hotelling, and so on. The principal angles between subspaces, here is a recursive definition, and the subspaces are called L and M. We find a vector in L and a vector in M that have the minimal angle between them. The vectors may coincide in which if there is a non-empty intersection. Keep them, write down the angle, write the two vectors, and now take all the vectors in L and M that are orthogonal to the previous pair. Keep doing this, find the next angle, and so on. So we'll find the angles that are increasing, and they can go from 0 to pi half. And these are called the principal angles between the subspaces. This is a nice way to look at this, but to calculate them, we calculate them using the singular values of the product of the projection on L and the projection on M. So this is a very well-known result. At least from 1955, some papers by Afriat in the Proceedings of Cambridge Philosophical Society. Now, if I take the product of these coselines, I use here something in bold letters, bad notation, and this, let's call it the product cosine. I take the sines and product, I get the product sign of the subspaces L and M. Now, this cosine square plus the sine square are not 1, so that's a bad notation. And here are some results. The Hadamard inequality is that if you have an n by n matrix, the determinant is less than or equal to the product of the Euclidean norms of the columns, with equality if they are orthogonal or include 0. The corresponding statement for the volume is that the determinant, now I break the matrix into two submatrices, A1 and A2, and the determinant absolute value of the determinant is the volume of A1 times the volume of A2 times the sine of the angles between the ranges. So this is a pretty result, but I don't think I cannot see that it will ever be used for anything useful. But we can talk about the Hadamard equality instead of the inequality. But here is another place where there is, when the result makes sense. If you have a bunch of vectors and you have their span, and you have any vector in the space, and part of it may belong in the span, but part of it sticks out, is orthogonal, the norm of that arrow, let's say, the part of the vector that is perpendicular to the space is the ratio of two volumes. The volume of the matrix made of the vectors V and W divided by the volume of the matrix made just of V. So that's a very nice result. Here is another result, a Cauchy-Schwarz inequality, and its generalization below is theorem 9. If you have two matrices, in this case a full column rank, the determinant of the matrices are B and C, so the determinant B transpose C in absolute value is the volume of B times the volume of C times the cosine, the product cosine of the ranges. This actually has been used. I was surprised, but some people call it volume correlation. So if you search for it, you'll find it. There are quite a few applications in electrical engineering and communications and so on. And the volume correlation is more or less the left-hand side divided by the two volumes. In other words, it is this. It is the cosine of RBRC. So you can do with it quite a lot. Okay, now, to put this in perspective, we have to go to higher. We have to go to multilinear algebra. And the basic product there is the exterior or wedge product. And these are its properties. It is anti-commutative, that is, the wedge of U and V is minus the wedge of V and U, and otherwise it is linear, distributive, and so on. So the kth exterior space over the original vector space has dimension n choose k. So this is the space of all k, of all exterior products of k elements in V. And we are led to the next topic called compound metrics. There are some other names for it. And this is if we take vectors x1 to xk and their exterior product, and then there is a matrix A that maps to another space, and we take the exterior product of ax1, ax2, axk. This is a linear transformation that goes from the product of the x's to the product of the ax's. So what linear transformation is responsible for this? And this is represented by something called the kth compound matrix of A. And it is a matrix, if A is m by n, this matrix is m choose k by n choose k, and the rank is r choose k. R is the rank of A. So in particular, the rth compound is of rank 1, because then we have R choose R. Okay, there are some nice properties of the compound. Nothing, so the compound of a product is the product of the compound, transpose, conjugate transpose, inverse, Moore-Penrose inverse. And the second line is due to Sylvester, so this has a name. All the others, I think, are accepted. This must be out of the mainstream because I could not find a program that will calculate the compound. However, Maple has everything that you need in order to write such a program. So here it is, and if you can improve on it, I'll divide it. And by the way, there's no way I can finish this lecture in 48 minutes, but I have about 80 unique slides. And this is a book in writing, so you are welcome to get the slides from me. There is a big bibliography menu with live links, so you can take the slides from me anytime you want. Okay, now here are some nice results about the compound. The definition of the compound: if A is n by n, then the nth compound is just the determinant of A. The determinant of A can be positive or negative, or zero. For the volume, I have the following result. The product, the compound matrix here should be plus or minus the volume of A. Because if you change one of these vectors, you negate one of these vectors, the sign will change. In other words, it would make sense at some point to talk about also negative volume, not just, or signed volume, maybe even complex volume. I'm not there yet. I'm sure that this would make sense at some point, and I see it from here. But I'm not there yet. Now, another name from history, from the 19th century is Blücher. And I give he wrote in English, by the way, and so I give his, he wrote in German, but there is a good copy in English, and so I give a reference to the work. But Blücher worked in projective geometry, but one of the results is that if you have a subspace in Rn, then it can be represented by a line, a one-dimensional subspace in the wedge product, in the R wedge product. of Rn, and it is denoted like this, W wedge. All it is the exterior product of any basis of W, any basis of W. So it is determined up to a scalar. Okay, now, if you have any two subspaces and you look at the matrices formed by their bases, then you take the Plicker coordinate of one subspace. All it is the rth compound of this matrix. You take the Plicker coordinate of the other basis. So the product cosine of the two subspaces is the actual cosine, the ordinary cosine of the Plicker coordinates. So that's a very nice property because it, in a way, preserves the angles. The cosine is the product of the cosines. Here is the maybe the ultimate singular value decomposition. Here is the picture of A written as U sigma V transpose again. Now what I do is that I take the rth compound of A, and A is rank R, so I will get a matrix of rank 1. A matrix of rank 1 is a product of a column and a row. And this is what I get. So that the rth compound of A is the volume of A comes out, and here I have the Plicker coordinate of U of the subspace spanned by U, that is the range of A, times the Plicker coordinate of the matrix made by the row of the matrix V transpose, and this is the Plicker coordinate of the range of A transpose. So this is a very elegant result. I'm not sure it will do good to anyone, but more about this in the future. So now, classical work of Gauss. Now, when I started my graduate studies at Northwestern, someone warned me from taking courses with Professor X because they said he's a 19th century mathematician. So here I am. I took the courses from him, and clearly I was influenced. Anyway, this is the beginning 19th century, that's 1827, the work of Gauss, very nicely translated by Dover. So there's a nice booklet about the geometry of surfaces by Gauss. So we take, this is phi is the mapping in the plane. He takes this rectangle into this shape, and Gauss defined three letters, E, F, and G. E is the Euclidean norm square of the gradient of phi with respect to x, so it is phi x dot phi x. G, the same for the gradient of phi with respect to y, and F is the product of the gradient of x and the gradient of y. Next come what Gauss called the first fundamental form. There is a second one which involves the curvatures, and the punchline is that the area, this area, dA, the area of phi of this area is the integral over this of the square root of EG minus F squared dx dy. Okay, so this is before Jacobi. So this is like a formula for, if you want, for change of variables in integration. Next, I will imitate this using something known as the Monge patch, or the Monge parametrization. So I take a surface in R3 and represent it with the Cartesian coordinates as x, y, and z, which is a function of x and y. So the mapping is then phi xy, xy, f of xy, and the Jacobi matrix is the matrix of partial derivative with respect to x or with respect to y. So this is phi x, phi y of Gauss. Okay, all it is you have an identity on top, and below we have the partial derivatives of f with respect to x and y. Then, e.g. minus f squared of Gauss is simply the square of the volume of that Jacobian. And that's why the area is, using Gauss, is the integral here of the volume of the Jacobian. Now the Jacobian now is not squared, the Jacobian is 3 by 2. In many examples I need the normal. And the normal is just perpendicular to phi x and phi y, to the gradients, and we can write it explicitly as the cross product normalized, because we want the unit normal. But if I look at the Jacobian, the 3 by 2 Jacobian, then it's easy to write the normal just by inspection, because the vector that is perpendicular to these two vectors will have minus fx minus fy 1. Now, how do I know that it is this vector and not reverse sign? I don't think in general I know, but I want to have like a right-hand system. This is why I think that z should be here, should be positive. But a priori, I wouldn't know if I want this vector or I want its negative. Anyway, the normal is then this vector normalized, so I divide it again by the volume, because the volume is the square root of 1 plus fy squared plus fx squared. And here is we are here to on the way to some lucky strike, because when I take the area, I have the volume up there, and if I multiply the area by the normal, as I often do, I have the volume down there. So there is a potential for cancellation, it actually occurs. In n dimension, this is not very different. You still have a surface, you need the normal. I use Monge parameterization or Monge patch. This is then the Jacobian. This is the function phi. This is the Jacobian, so it is not squared. It is n plus n by n. And again, I can read from it the normal, and here it is. Still in the 19th century, we go to Jacobi, the famous change of variable in integration result, and it can now be done using this volume with less work, let's say, because the integral of f, the function f, in here, let's say in the surface S, which is phi of its projection on Rn, this integral is the integral in Rn of the function fx y and small fxy times the volume dx dy, times the volume of this Jacobian, which is rectangular. Here is the cancellation I mentioned. That is, when I want to integrate a vector field, a force field, then I have the result is that this is the dot product of the force field and the normal times the area element, and now I get the cancellation of the volume. So I get a very nice result for the integral of the force field. Okay, we can do it with other coordinates and get the Radon transform is another important integral. That's the integral of a function over a hyperplane. And again, the volume allows us a nice simplification. I want to show you now some results that are, at first sight, they look weird. They concern the unit ball and sphere in Rn.